All right, our next talk is going to be on a flexible approach to modeling unpredictable events in MDPs by Stefan Witwicki, Francisco Melo, Jesus Capitan, and Matthijs Spaan, and the talk is going to be given by Stefan.
Hi everybody, once again my name is Stefan. I'm a postdoc at UNESCO ID, which is an institution that's affiliated with the Instituto Superior Técnico in Lisbon, Portugal. And today I'll be presenting joint work with my European colleagues, Francisco from Portugal, Jesus Capitan, who's currently at the University of Duisburg-Essen in Germany, and Matthijs Spaan at TU Delft. So at this conference, we all know that planning is hard. MDP planning in particular has a reputation of being challenging, but so is modeling. And this is especially true in dynamic environments where events are hard to predict. So this paper is about how we can formulate the MDP model as a precursor step to planning. And in particular, I'll talk about strategies for modeling hard to predict events by exploiting factored structure that simplify the specifications of the transition model, as well as by applying Bayesian inference to reduce this factors representation into something that's potentially more compact and also more robust to precision. So I'll get into those details after motivating the problem in a concrete robot planning domain. Then I'll present our main theoretical result along with a method for using the theory, and I'll close with a summary and discussion of our ongoing work. So this particular work comes from a project called Multi-Agent Intelligent Surveillance Systems, MISE-S. And we're working in close collaboration here with a company that deploys video surveillance systems in shopping malls, for instance. And the idea is to augment the conventional system and to replace the actions and decisions of human security guards with machine intelligence. So this intelligence comes both in the form of computer vision algorithms that might automatically detect suspicious activity. The intelligence also comes with robots that would replace the mobile security guards. And so as a playpen for our robots, here we've turned the entire floor of an institute for systems and robotics in Lisbon into a mock surveillance environment. We have a dozen cameras set up around the floor. Here you see the video wall view of the system. And you can see people have these blue boxes, which are detecting people as well as other kinds of things. So for instance, here in the upper right, you see a person waving, and that's detected as a particular event. And added to this system here, we have a Pioneer robot. I should mention the robot is using low-level control algorithms that are off the shelf using ROS, the robot operating system. That allow it to avoid obstacles and to invoke a simple path planner to do a waypoint-to-waypoint navigation. But in this talk, when I say planning, I'm talking about higher-level planning. So what areas should the robot visit? What high-level activities should it pursue? So for instance, here we see the robot moving around the map, simply patrolling, surveying various rooms of interest. And in addition to this kind of patrolling behavior, the robot should also plan to respond to various events. So here we see a visitor, yours truly, that has entered the floor and is waving to the cameras. And now this event is transmitted to the robot, and if it has a plan to attend the event, then it will go. And in this case, it just goes and it meets the person, and it offers assistance to the person. So for the robot planning, we've chosen to apply a principled framework, Markov decision processes, or MDPs. And this allows us to formulate robot decision-making as an optimization where we can balance different objectives, such as patrolling and responding to events. And we can also account for the uncertainty in this dynamic environment. So very, very briefly, oops, that's not right. So very briefly to review the MDP, we represent a random variable S, that's the state of the robot. In the case of a partially observable MDP, the robot doesn't observe S, it instead observes another variable O. But for this talk, for simplicity, we'll stick with fully observable models. The agent then takes an action, A, and transitions into a new state. And this transition is valued with a particular reward that somehow encodes the objectives of the problem. And then this sequential process continues, a new action, a new transition, for either a finite number of decision stages or else for an infinite horizon. We can also encode this Markov decision process using a two-stage dynamic Bayesian network that represents the dependencies among the variables. So here we have the state at stage t+1 is dependent on the previous action and the previous state. And this, in fact, there's a probability of next state given action and previous state that's encoded in the transition matrix. And so whereas most of the work at this conference focuses on the planning, that is taking the problem and computing a good policy, the problem of modeling is often entirely overlooked. It's easy to take for granted that we have a good MDP model of our problem until we actually try to apply this stuff to a real system. So how do we construct the model? Where does the transition matrix come from? Well, it might come from known dynamics. So if we're playing poker, we know the exact probability of drawing a 3 of spades from the deck. Transition probabilities might also come from expert knowledge of our domain. Or for some problems, what we can do is conduct repeated trials and try to learn the transition model. Nevertheless, modeling a problem as an MDP is non-trivial. And to go through an example, let's try to formulate the robot decision-making problem as an MDP. So it's often useful to take our state and treat it as a list of features to factor the state. So here we've represented feature F, which is the fire status, also the robot's position P, and we should choose an appropriate level of abstraction so that the robot is not planning necessarily precise locations in the environment, but instead at a higher level, the room or the corridor that the robot is currently located. There's also a state factor that represents the surveillance status. For instance, how recently each of the positions was last surveyed. And also we can encode events such as whether or not there's a visitor waving as a state factor. And with this factored representation, it also gives us sparse transition dynamics. So instead of encoding all of the transition probabilities in one big table, we can split it up into individual conditional probability tables, where here, for instance, the next position of the robot is actually independent of whether or not there's a visitor waving. But in this talk, that we contend that some of these factors correspond to the events which are inherently unpredictable. That is, their transition probabilities are hard to specify. So in our robot planning domain, one example of such an event would be the fire. In this case, fire dynamics aren't known a priori. We don't have a fire marshal coming and telling us, oh, this is exactly the probability of a fire breaking out in this room. And for this kind of an event, we don't want to wait around long enough for enough fires to break out so that we can compute a precise estimate of the fire probability. So what do we do? As a first step to trying to model an event like a fire, what we could do is to try to model the fire process itself. So, for instance, if we restrict consideration to fires caused by a coffee machine, we could think about whether or not the coffee machine is on. Fire might also be related to the condition of the wiring and the humidity in the room. So here what I've just done is to add extra features to our model. These are the factors that underlie the event that we're trying to predict. And so this helps us to formulate a predictive model of fire, but it also adds to our state space. With every new feature, we have a potential exponential increase in the state space size, which makes planning then more costly. But a key theoretical result that we've derived is that no matter how many of these additional factors we add, we don't actually need to keep them around when we go to plan. These factors the factors that aren't observable, the latent variables, can be safely removed. For the purpose of planning, we can maintain the same predictive power with only our internal factors. However, we may need to augment our MDP state space with histories of observable variables. So for POMDP people, this shouldn't come as a big surprise. For a POMDP, the history of observations is a sufficient statistic for planning. Thankfully, in the paper we go into a bit more detail, but depending on the factored structure in our problem, it may be that not all history is required, only histories of some of our state factors. And in this paper, we provide an algorithm for taking those external factors and removing them. And we accomplish this through Bayesian inference. What we can do is simply to marginalize them out one by one, starting at stage 0 and progressing forward. And we're left with conditional probability table of F that's independent of our external variables. And so taking a step back, what I've just described here is a two-phase process for modeling. So first, we expand our model by adding variables underlying the events, and then we infer a reduced model. And we argue that this can simplify the modeling problem because we can specify those dynamics of underlying variables one by one, and then we can take advantage of Bayesian inference to automatically aggregate those dynamics and to reduce our model. And as I mentioned, this has the potential for reducing planning complexity as well, depending on how many variables we eliminate. So recall that a key motivation for this was handling unpredictable events. And so I've just given you one strategy where we simply add external variables and make those events predictable. But there's a problem here, and it's that what if the variables that we add are themselves unpredictable? So maybe one of the variables, C, itself would require external variables to better predict it. So we can see that by modeling underlying variables of the events that we're trying to predict, this kind of recursion can really blow up in our faces. And ultimately, we should draw the line somewhere. It turns out that we can draw the line by acknowledging this limitation and saying that for some variables, for instance, C, we can instead specify a bound, acknowledge the fact that we don't have a precise probability. And we can use the same inference algorithm then to propagate that bound, just as we did with the precise probabilities. Only now what we're left with is a bounded parameter model. This was first studied by Givendine and Leach. In fact, we're representing a whole space of possible MDP models, which gives us some robustness to imprecision. So to conclude, the problem that we've addressed is how to construct models for planning in dynamic uncertain environments. And we've proposed a two-phase approach where we introduce external variables, then specify probabilities over those variables or bounds on the probabilities, and then marginalize them out. And this allows us a couple of advantages. First, we can highlight those variables that are the primary sources of unpredictability. So it may be that only one of the variables requires a bound, and depending on how much domain knowledge, we can tighten our bounds and get better predictions over our event variables. And so you could view this work as a precursor to work that develops these bounded parameter models and algorithms thereof. So really, we're taking a step forward toward applying the MDPs. And although the contribution of this paper is mainly theoretical, we do have some ongoing empirical work where we're looking at evaluating policies coming from our BMDP. And so because the BMDP includes uncertainty and represents a whole space of models, there's also a space of potentially optimal policies. So here you can picture this space where the boundaries are really optimistic and pessimistic MDP models. So there's still the question of, given this space, which policy should we pick? And one other piece of ongoing work is, I mentioned that through the inference process, we could be introducing history dependence. And this is not going to scale to infinite horizons, or even to medium length horizons. And so currently we're looking at approximation techniques that eliminate some or all of this history dependence. And we're particularly interested in approximations that we can theoretically characterize. So we know that there's a trade-off with quality and computation. And to better assess this trade-off, it's nice to have bounded approximations. Thanks for your attention.